Hey everyone, how are you? In this video, we are going to solve the Leetcode problem of the day, and the problem is fruits into basket part 3. Now the part 3 of this problem is of medium level and the part 2 of the same problem was of easy level. Basically the part 2 and the part 3 are the same problems but with different constraints. Basically the part 2 is easy because the given input has a lower constraints. The number of inputs given in the integer arrays are going to be less for part 2, and that is why it is easy because it can be solved by brute force. If you just brute force your algorithm and try to solve it, part 2 will be solved. But the part 3 cannot be solved using brute force, and that is why part 3 is of medium level. In this video, I will tell you the brute force approach, and I will tell you why this will not work and what is the best approach to solve problems like these for all the given constraints. In this particular problem, the given input is an integer array called as fruits and another integer array called as baskets. Both the array will have the same length, and what we have to do is the output we need to give is the return the number of unplaced fruits. Basically, we need to place the fruits into the baskets and we need to find out the number of unplaced fruits. Now let us try to understand the problem using an example. So in the example, the fruits are given are 4, 2 and 5, and the baskets given are 3, 5 and 4. In the fruits array, the given numbers are representing that how many fruits are there. For example, this particular data is telling me there are 4 fruits, and the baskets are telling the capacity of how many fruits it can hold. So this basket can hold 3 fruits, this particular basket can hold 5, and this can hold 4. Now if you want to find out the output for this particular input, you need to find out the number of unplaced fruits. Basically, if you can place these 4 fruits into a basket, then it is placed. But if you cannot place these 4 fruits into any of the basket, then this is unplaced. You don't need to count this as 4, you just need to count it as 1. That is, if you are able to place all the 3 fruits in the different baskets, then the number of unplaced fruits are going to be 0. But let us say you are not able to place this particular fruit into any of the basket, then the total number of unplaced fruits are going to be 1. Basically, you need to count this as 1, this as 1 and this as 1 and not 4, 2 or 5. Now there is a rule that you need to place a particular set of fruit in the leftmost basket which can hold these many fruits. That is, if you want to put these 4 fruits into any of the basket, then you cannot place it randomly. You will have to place it in the leftmost basket which can hold at least 4 fruits. It means that you cannot put 4 fruits into this basket because the capacity is 3. But you can put these 4 fruits into this particular basket because the capacity is more than 4, right? It is 5. So this particular basket can hold this particular fruit. So now let us solve the problem and let us see what is the brute force approach, and we will talk about why this will not work and what is the correct process to solve this particular problem. So let us try to first place this particular fruit 4. It cannot be placed in the first basket because the capacity is less than 4, but this can be placed in the second basket because the capacity is more than or equal to 4. So we can say that the fruit number 4 is placed on the basket number 5. Now let us talk about the next fruit which requires a capacity of 2, right? So let's start searching from the left, and the first basket is having a capacity of 3. So we can put this particular fruit in the first basket which has a capacity of 3. So this is also placed, and now this is occupied. Basically, you cannot put 2 different fruits into one basket. So these 2 baskets are occupied, these 2 fruits are placed. Now let us talk about the last one which requires a capacity of 5. Let us start searching from the left. This one is already used, this is already used. We just have one basket left and the capacity is less than 5, right? So we cannot put this particular fruit into this basket, and we don't have any more basket. So this particular fruit is not placed. The number of unplaced fruits are 1. So the output in this particular scenario is going to be 1. That is our final output. Now how can you solve this using brute force? It is very easy, and this was the problem of the day yesterday. See, the simple method is you will start from the left. You will see that okay, it requires a capacity of 4. Let's go from the left and let us see which basket first will have the capacity of at least 4. Alright, so we got a basket, this one, and what we will do is we will say that this is fine. As of now, our count for the output is 0. That is, we have not found any unplaced fruits. But now this particular basket is used. So what you can say is let's make its capacity as 0. This 0 indicates that it has no more capacity left. So this particular basket is used so that it cannot be used later. Similarly, now for this one, we will start from the left. We found a basket which can be used to store this particular fruit. So we are going to store this, but now we are going to mark this particular basket capacity as 0. Now let's talk about this particular fruit which requires a capacity of 5. It has a capacity of 0, it has a capacity of 0, it has a capacity of 4, which is still less than 5. So this cannot be placed. So from here we can, so at this point we will count our output as 1. Our output will be 0. The moment we found a fruit which cannot be placed, we will make it as 0 to 1, the output. Now we are done processing all the fruits and the final output is 1. But this is the complete brute force approach where for each of our fruit, we are checking the entire baskets. So the time complexity of this is O of n square, where n is the number of fruits or the number of baskets. For each fruit, we are running the entire loop n times, right? That is why the time complexity is n multiplied by n, which is n square. This will work for fruits into basket part 2 because the constraint was very small, but this is not going to work for the part 3, which is the problem of the day today. So we have to think of an algorithm which is less than n square. And we can actually solve this problem in n log n time complexity. This whole problem actually screams about a data structure which is called as segment trees. Now, first of all, you will need to understand that why segment trees is the best data structure to solve this particular problem. See, the thing is, before you actually solve this using segment trees, you should know about this data structure. If you know about this data structure, after looking at the problem, you might understand that, okay, this particular data structure can be applied. So let me tell you about this particular data structure called as segment trees. Let's try to read the question again. What we are given are, we are given some fruits which requires some capacity, and based on the capacity, they can be stored in a particular basket. We are given baskets which has capacities, right? Now for each of the fruit, we need to find from the leftmost that which basket has a capacity more than or equal to the fruit, right? So the key operations which we need to perform is, we need to find the leftmost, right? The leftmost basket with value which is more than equal to the fruit, right? And the moment we find a particular basket, we are going to assign our fruit into that basket, and then we are going to update the capacity of our basket to 0 so that it cannot be used later on. So now we need to update the basket, right? From here you will see that you need to do two operations. The operations are, first is a query. You are searching for something, you are searching or making a query to find something, and then you are doing an update. Segment trees are exactly about querying and update. Querying your data and then you update your data. That's what segment trees are all about. Basically, we need to search or we need to query from a range. The given range is our baskets, right? So if I talk about the summary, that why should we worry about this particular data structure and why should we think about this data structure? First of all, you should know this data structure, and then when you read the question, you will find that you need to do a fast lookup. You need to do a fast query to find the valid basket from a range of values. And the moment you find a value, you need to update that value, right? And you want to preserve the order as well. You don't want to sort it, right? The moment you sort it, your leftmost data is not the leftmost data now, right? And you want to enhance the performance. You want to better your algorithm time complexity. And the time complexity for segment trees are n log n. This log is to the base of 2. So now our complete focus will be to understand that segment trees data structure. And once you understand the data structure, solving this will be a piece of cake. What happens is, we have to first identify our range. Our range is 3, 5, 4, right? I will try to build this particular tree. And if you don't know about a tree, and basically segment trees are binary balanced trees. Now when we say it is a binary tree, it means that it will have two children. Every node is going to have two childs. And when we say it is a balanced tree, it means that every node will be filled with all its children apart from the leaf node. And the leaf node will be leftmost possible in the left hand side. Let me show you what I mean. If this is your root node, that's our root, then you will have the children of this root node, right? There will be a left child and there will be a right child. So now this is a balanced tree. As of now, the leaf nodes are L and R. They are our leaf nodes. And you will see that every node is having at least two childs, but the leaf nodes are not having two children. That is why they are called the leaf nodes. Now let us say there is another tree. There is a root, then there is a left node, then there is a right node. Now let us say there are three more nodes, three more data. So you will start filling three more data into this tree. So you will say that this is the data number 1, then we have a data number 2, then we have a data number 3. So now you will notice that every node are having two children. The non-leaf nodes are having two children, but the leaf nodes are having 0 children. And all the leaf nodes, 1, 2, 3, they are as left as possible, right? If I put this 3 in the right side, then this is not valid. So segment trees are all about binary trees which are balanced. So now we have to create balanced binary tree, and we will see that how this balanced binary tree, how this segment tree is going to help us solve the particular problem. What we are going to do is, we are going to put these nodes or these data, the data which we need to process, as the leaf nodes. Now let me try to build the tree, and while building the tree, you will find the solution itself. Now let us say we have just one basket. If we have just one basket, which is 3, then this is one of the data we have, right? Now if I ask you that I have fruit which requires a capacity of 8, can you find it? Can you find a basket? You will say that, okay, let me look into our data. And no, I don't have a data which has a capacity of at least 8. Alright, now let us say I have another data which is 5. Let me put it here. If I have two data and I have to search for the same thing, what you will do? You will say that, let me look into the first one. Now let me look into the second one. And I didn't find any data which can hold the capacity of 8. It means I have no baskets which can hold the capacity of 8, right? But now you have to check both the baskets, right? What if instead of checking both the basket, I can create a tree and I can say that they have a root node and the root node will have the maximum value. The value is 5, right? Now if I ask you, can you check that do you have a capacity to hold 8? So you will check the root and the value is 5. The maximum is 5, so you don't need to go further. Because if the maximum cannot hold, then the children cannot hold the capacity 8, right? But if somebody asks you, can you hold a capacity of 4? Your maximum is more than or equal to this required capacity. So yes, 4 is possible, definitely. But where exactly are you going to place? This 5 value is a virtual value which we created. But the actual basket values are here, right? So now when you get a query for 4, you will go down and in both the direction, in left and right. But you will first go in the left side. Reason being, you have to search from the leftmost data. Now if you want to search for the leftmost value for the capacity of 4 and the left data is 3, it cannot hold. So now let us go to the right one. So what will happen? The right capacity is fine. And this is the leaf node. If it is a leaf node, it means that this is my actual basket value. This is not a virtual value which we created. So it's a leaf node. and this node is going to hold this value 4. So now what we can do is we can say that this value 4 can be holded in this particular basket, and then we need to do the update. We can say that this 5 will be updated to 0 because we have used it to store a capacity of 4. So now the maximum of this will be 3 and not 5, right? So we are going to update it in the parent as well, and the parent will be 3. Now if I ask you, can you hold a capacity of 4? You will say no, because the maximum value cannot hold the capacity. This is exactly what you need to create for all the data. Now, how many leaf nodes you are going to have, how many parent nodes you are going to have, that is something which you will understand, and I will explain you. First of all, let me create the exact tree. So what will happen? You will have your nodes. You will have your actual basket capacities as the leaf nodes. So let me create the leaf node. It is 3, then 5, then 4. Now for 3 and 5, the maximum is 5, right? So we will create a parent of 3 and 5, and it will be 5. Now for 4, you need another value to compare it with, right? But you do not have. See, the thing is, in a balanced binary tree, every node is going to have 2 children apart from the leaf nodes, right? The leaf nodes are not going to have any children, and the leaf nodes are as left as possible. If you don't have any more value to compare it, let's assume that there is a value, and that value is a 0. So we are going to create a virtual value, and let's make it as 0. So now you have a 4, you have a 0, their parent will be 4 itself because the maximum is 4, right? So now you have 2 more values, 5 and 4. They are separate trees. Let's join them again with another parent node. What you can do is you can add another parent node, and their value is going to be 5. Reason being, the children are having the values as 5 and 4, so the parent will have the value as 5, right? Because 5 is the maximum. Now let us start doing the query. This is our whole tree which is created. I will tell you the logic of creating this tree, but let us say the tree is created. So now what you will do to search for each of the fruits. First of all, you will get the fruit 4, right? You will search for the parent. The parent says the value is 5. If the value is 5, it means that you definitely have a capacity to hold this value 4, right? You will first search in the left hand side. Reason being, you have to fill the leftmost basket first. Alright, this is a 5. I need a capacity of 4. I got a capacity of 4. Let's go in the left hand side. Does it have a capacity of 4? Yes, this has a capacity of at least 4. So now we again go to left hand side, but this time it doesn't have a capacity of 4. So now we need to go to the right hand side, right? So at this point we got a leaf node, and once we get a leaf node, we need to fill this particular value. We will fill this particular value with 0. So now the parents are going to be changed, right? The parents are going to be updated. The parent of 3 and 0 is going to be 3. The parent of 3 and 4 is going to be 4 now. But at this point, we have this 4 fulfilled. Now the next value to search is 2. Do you have a capacity of filling 2? Yes. Is it in the left hand side? Yes, it is in the left hand side. Is it in the left hand side? Yes, it is in the left hand side, which is 3 itself, right? So now we update the value of 3, and we are going to say, hey, this is 0. So the parent is now going to be 0, and the parent of 0 and 4 will still be 4. But we have fulfilled 2 as well. Now we are going to search for 5. The parent says that the maximum capacity is 4. We cannot fill this value 5, and we are done. We got a value which cannot be filled. This is the whole logic of solving this particular problem using segment trees. Now let me show you how can you create these segment trees, because they are not created exactly like a tree. They are created like an array. We first need to store our leaf nodes, which are basically our actual data given in the basket. So we are going to store our data as 3, 5 and 4, right? Now for 3 and 5, we need another data storage, right? We need to store their maximum, which is actually going to be 5. For 4, we need another node, 0. Again, I will tell you why we need this node, but let us say we need this node, right? We need pairs. We need a pair to store their maximum, right? So as of now, we have a pair of 3 and 5, and for 4, we didn't have a pair, so let's assume it is 0. For 4 and 0, we will store the maximum, which is nothing but 4. And for 5 and 4, we need to store the maximum, which is 5. So now we need a capacity of at least 3, which is the number of basket elements we have. And we need to make sure that every element in the basket has its pair. So for 3, the pair is 5. For 4, we don't have a pair, so let's make it as 0. So we need at least 4 capacity. Now for every 2 capacities, we need another capacities, right? For every 2 capacities, we need another capacities. So there is a simple formula to find out how many elements can you have in a balanced binary tree in which all the leaf nodes are filled. It is actually 2 is to power h minus 1. H is the height. The height of the binary tree is 1, 2, 3. The height is 3. So we need at least 2 is to power 3 minus 1, which is equal to 7. It means we need a block of storage of at least 7. So we are basically going to use an array or a list of 7 elements. But instead of 7, let us store at least 8 elements, which is actually a power of 2. What we will do is we will say that this is our index number 1, then 2, then 3, then 4, then 5, then 6, then 7. Index number 0 can be ignored, but let's store this. So what we are going to do is we are going to create an array of size exactly double of the number of leaf nodes we have. Now, first of all, we need to find out how many leaf nodes we need. We need number of leaf nodes, which is the power of 2, so that every element has a pair of it, right? Now, as of now, we have 3 elements, right? If we have 3 elements, what power of 2 makes 3? So basically, we need to find the log of 3 with the base 2, and it will be 1 point something. Let us say it is 1 point x. So now we have to take the ceiling value of this, the maximum of this. If it is 1 point x, let's make it as 2. Reason being, if we make it as 2 and we say that we need 2 to power 2, that is 4 number of leaf nodes, then that will be correct. Because originally if we will have 4 elements, let us say we have total 4 elements, then every element has its pair, and log of 4 to the base 2 will exactly be equal to 2, right? So first we will calculate the number of leaf nodes required, and then we will create an array of size double of the number of leaf nodes to store its parent nodes. Once we store the parent nodes, first we will create this segment trees, and then we will search for every element of our fruits in this segment trees, and then we will keep updating our segment trees the moment we find a particular basket which has a capacity to store a particular fruit. So now let me take you back to the code editor and let me show you how can you code this using Python. First of all, we need to understand the logic of segment trees. Basically, what we need to do is we need to create a tree, right? And this tree will be equal to the segment tree, and we will pass our baskets data into this. So first there is an init method which is going to store our initial data for the segment tree instance. So first of all, we need to find out how many leaf nodes do we need. So we just need to take the length of our data, that is how many number of baskets we have, then take the log of it with the base 2, then take the ceiling value, and then 2 is to power that particular value will tell me how many exact number of nodes we will need for each node to have a pair. Then the number of elements we need in our tree will be self.tree. Let's create a tree, and let us say we create an array of total 2 into self.n. That is how many leaf nodes we have. Double of that will be the number of nodes in our whole tree. Then we will try to update the data for the second half of the tree. What we will do is we will put our basket value in the second half of our tree, and we will keep updating the first half of our tree, which are going to be the parents of each pair nodes. So we are going to say for i, value in enumerate our data, let's update our data self.update at which index, at index of I plus self.n. These are the second half of our tree with the values. The values are coming from the basket. What do we need to do in the update method is we have an index at which we need to store the value. So we will store the value directly at the particular index, and then while the index is more than 1, that is while we keep updating the parents, we will say that let's try to update the parent of the current index. The parent of the current index will be index divided by 2, because these will be stored at the index of 4, 5, 6. So basically this is at index 4, this is at index 5. The parent of 4 and 5 will be stored at index 2. Here we will have index 2, then we will have index 3, then we will have index 1. Index 1 at the top, then index 2 and 3, which are the parent of 3 and 5 and 4 and 0. Then index 4, 5, 6 and 7, which are 3, 5, 4 and 0. 0 is basically added here to complete the pair of 4. So we keep dividing the value of index with 2, and every time what we can do is we can store the maximum of self.tree at index 2 into index and at index 2 into index plus 1. Basically the child nodes for this particular index, we will get the maximum value of the child nodes for this particular index. We will update it, and this way we are going to create our tree. Next is we want to find out how many unplaced fruits we have. So we run a loop in our fruits, and we say that let's try to find out which index can store the value of this particular fruit. That is which index has the capacity to store this particular value. That will be done using the find method. I will explain you the find method, but the thing is the find method is going to return -1 if it cannot be placed. It will return a particular index if it can be placed. So if the index is -1, unplaced plus equal to 1. But if the index is not -1, we are going to update our tree, and we are going to say place at this particular index -1. So this is going to update the whole tree, and then we are going to return unplaced, that is number of unplaced fruits. Now talking about the find method, it is very simple to understand. First of all, we are going to check our root node. If our root node is less than the data, it is -1. That is, we don't have a capacity to store this particular fruit. But if it is not -1, if it is not returning, then we have a capacity, and let's start with the root node. The root node is at index number 1, and while we have an index which is less than self.n, we are going to keep finding its child nodes which can store this particular data. That is, we will keep finding till the nodes which are leaf nodes. We will not search below the leaf nodes. So now if from the self.tree at index 2 into index is more than data, it means that we are first going to find out, so whatever is the index 1, we are going to first go to the left child, which is at index 2 into index. If that value is more than equal to data, we are going to update our index, which will be equal to 2 into index. That is, now our index will point to the left child of our root node. But if the left child capacity is not possible, then let us go to the right child, which is at index number 2 into index plus 1. So we will keep continuing this particular process to find out which leaf node can store the value. We will return that particular index so that that particular index could be updated. This is the complete process to solve this particular problem, and what I will suggest you guys is to focus more on the segment tree part. This particular part of the code is very simple, but the main part is to understanding the segment trees. So I will suggest you to understand the segment tree data structure and its code, and everything will be clear for you for this particular problem. So that's it for this particular video, guys. Let me submit this, and this is going to pass all the test cases in a very efficient manner. So this is the perfect solution for this particular problem. You can see that the runtime is really good, the memory used is really good. So we have solved this particular problem. Now, if this video helps you to understand the problem, why we are using segment tree, what's the intuition behind this, how segment tree can be applied here, if all these questions are answered for you from this particular video, then make sure that you hit that like button. And if you are not subscribed to my channel as of now, then make sure that you subscribe to the channel as well. And I will see you guys in the next video. I want to see you guys in the next video. Thank you for watching this one, guys.